Okay, good afternoon. You probably saw the announcement that in the end we will have 1 hour of lecture today and 1 hour with Neta. And we're discussing the binary perceptron. And I would like to start by reminding you what we discussed last time. So we discussed the capacity of the perceptron, which is given a set of p points in the n-dimensional space, which are on a general position. How many of the dichotomies? There are 2 to the p dichotomies, right? And we discussed how many of these dichotomies can be realized by a binary perceptron. And I mentioned to you Cover's theorem that answers this question, and you will prove Cover's theorem with Neta later today. But then it gives you it gives a formula, and we just analyzed what this formula is telling us. And what this formula was telling us is that if p is smaller or equal to n, p is the number of points n is the dimensionality of the space, the number of inputs. Then if p is at least is smaller than n or equal to n, then and these p points are on a general position, then a binary perceptron can realize every possible dichotomy. So C, in this case, C p n is equal to 2 to the p. And that's one thing that we saw. And then we saw that if p is equal exactly to 2n, then C p n turns out to be exactly half of 2 to the p. And if p is much larger than n, then Cp of n is much smaller than 2 to the p. And then the last thing that I did is I plotted the capacity normalized by the total number of possible dichotomies, 2 to the p, as a function of p. And so what we know is, and so let's plot it now. I didn't do it like this. I don't remember if I did it explicitly like this last time. Let's plot it as a function of p divided by n. Okay? So now when up to p divided by n equals 1, this is exactly 1, right? And we know that when this is equal to 2, it's exactly half. And the last thing that we know, that the last point, is that when it's much larger than 2, it's close to 0. And then what I told you without proving is that, in fact, when n becomes large, so now there is a whole family of plots like this depending on n. Okay, the one-dimensional case, two-dimensional case, and so on. For large n, it turns out that this curve approaches a step function. So for large n, it really becomes something like this. This would be large n. And for smaller n's, it's more smooth. So For small n, still for all of them, this is precisely 1 here, and then for smaller n, there is a more gradual transition, but this would be small n. I don't have an answer to this right away. I should think it's a good question, but whether there should be some intuition, but I don't know. The only intuition that I can mention is that for those of you who studied physics, it's reminiscent of the fact that in statistical physics, systems with a large number of degrees of freedom can develop phase transitions, which are sharp transitions as a function of some parameter. And in fact, there is a way to connect the question of capacity of the perceptron to a formalization which is within the formalism of statistical physics. And so it is related to phase transitions in physics. But this is a very kind of abstract answer to your question, and I think you're looking for a more intuitive way to understand, and I don't have a good answer right now. I will think about it. Okay, so one thing to remember about this result is that you can think about this quantity as like, what is the probability that if I choose some dichotomy, it will be realizable, right? One thing to remember, though, is that this is under the assumption, if I interpreted this as this probability that a dichotomy will be realizable, this is true if the dichotomy is chosen completely at random, right? If really, if we draw for each point along of the p points independently of the others, whether it should be classified as 1 or 0, then this will be the probability that what we get can be realized by a binary perceptron. Oftentimes, the dichotomies that we need to realize in reality have some are not like that. The points that are close by in space are classified, should be classified in a similar manner. And so if you draw your dichotomies not from this distribution of random dichotomies, but some other distribution, then this is not necessarily the probability that it will be realizable. Okay. Next question, which I will not touch on deeply, is the question of generalization. So, in some sense, this capacity tells us what is the space, what is the number of the number of possible dichotomies that our network can realize. It's sometimes called the complexity of the architecture, the space of different functions, in this case dichotomies, that can be realized, and so if the dichotomy is large, if n is sufficiently large compared to p, a binary perceptron will be able to realize every possible function. But I remind you from what we talked about earlier that what we really care about is generalization. Okay, the fact that we can learn every possible dichotomy is not a good thing. It's not necessarily a good thing, because that means then that if we would add another example, our architecture would be able to realize every possible answer on it. So what we really care about is if we see a certain number of examples and set our network or our perceptron to realize the answers that we want for these examples, will it generalize correctly to other examples? it's not clear what this. I mean, this depends on many things. It depends on the distribution of examples. It depends on the distribution of points. It depends on the function, on the type of a function that we want to approximate, and it's not obvious that one can make some general statements about these questions. It turns out that there are some interesting mathematical rigorous statements that can be answered, that can be made about generalization, and we will not discuss them in this course, but this is a topic of statistical learning theory. Which we will not go into. And I will just mention one quantity that you might hear mentioned, but I will not really discuss why it's important. I will just make the definition so that you know what it is. It's called the VC dimension. Maybe I will just write down what it is. It's defined as the maximal number of points P for which the architecture can realize all the dichotomies sometimes in the jargon of statistical learning theory, this is called, it can shatter all dichotomies. And so for the linear perceptron, for the binary perceptron, sorry, what is the VC dimension? Yeah, it's equal to n. Okay, but so as I said, I'm not going to go more deeply into this. But if you're interested in statistical learning theory, there are courses in the computer science department that you can take. Now, next question that I want to raise is the following. So we found that there is a certain fraction of the dichotomies that can be learned. How can we learn them? So remember that for the linear perceptron, all we needed to do in order to find the best solution, the weights, was to invert some matrix and multiply it by some vector, and we had the weights. What should we do here in order to find a set of weights that realizes a given dichotomy? It turns out that there is a fairly simple algorithm that can be applied in order to do this, and it's called the perceptron learning algorithm. And I will just describe it to you, okay? So, the idea is the following. We start maybe I will just draw the architecture that's just so that you will remember. We have our inputs, x1 up to xn. I think I switched today from large n to small n, but that's okay, right? Because we don't have different uses for them. And we have our output unit, and it's connected with weights, W1, W2, up to Wn. And let's call this y. And so y is the sign of W transpose x. Right, and now I give you p points. I tell you for each one of them. So we have some examples. So we have some examples. X mu, y mu. This is plus minus 1. And we want to find a set of weights that will realize this dichotomy. Okay, so the algorithm is start from some random choice, whatever you want. Start from some weight, W0. The only important thing is that this will be not be 0, not be a vectors of 0. Okay, so you have to choose some weights as a starting point. By the way, why is it bad to start with weights which are why are weights which are 0 bad?
Then why would it be 0?
Because then this thing is not well defined, right? We need to have some answer which is which are so strictly speaking, we even need in order for the output of this for this thing to be defined for every input. It's not just that the W doesn't need to be a vector of 0. All the elements of W should not be 0. Maybe I think it's a more correct thing to write. So W0, all Wi's. Because otherwise you can have an input. If there's an element of W which is 0, you can have as an input a vector X which has an entry only on that direction, and then this thing is 0, and then it's not defined.
Yeah, but you can have 0 inside the sign in other occasions, like anything perpendicular to the sign. If you have an example that is, you have to define somehow the sign 0 outside.
Yeah, it's true. But anyway, you start with a W which is not 0. You wanted to ask something?
No, I wanted to say that.
Okay, so that's a good time then to. I don't have a pen. Someone will need to. Let's see if this works. Yeah, this works. Okay, that's a good time to write your name.
I'm sitting in the same place.
Okay, so.
More or less.
Lior?
Leo.
Yes. Okay, good. And Guy. Okay.
Usually sits next to me.
You're more or less in the. You were a bit more. When we took the picture, you were a bit more to the left. Anyway, you choose a W which is not 0. And now you do the following. So the idea is that we kind of go through all the examples. We iterate through all the examples. And in each iteration, we may update our weights. And so let's call WT the weights after seeing T examples. And WT and WT plus 1 will be updated from WT based on XT plus 1, YT plus 1. When I write XT plus 1, YT plus 1, what I mean is that we go cyclically through these examples. So this can be more than P. 1 to P, and then P plus 1, it will go back to 1. So that's what I mean. I think it's clear enough. And now, what is the update? So, if YT plus 1 times W transpose T, WT transpose times XT plus 1 is larger than 0, what does that mean? What this means is that the classification made by our perceptron with our previous weights, WT, matches the desired output. If it's 1, then, I mean, two possibilities. One is that this is 1, and therefore the sign of this is 1, and this is also 1. And the other possibility is that this is -1, and this is also -1. Both are okay. In both cases, this means that we are classifying, based on the previous weights, the next example. And in this case, we just don't update. In other words, WT plus 1 is equal to WT. Okay? Yes?
Didn't we already found the formula for W optimal that we can just take all the examples and
How?
use them?
How did you find it?
We did it, right?
No, this was the linear perceptron. This was a case where the y was not a binary variable. It was a continuous variable, and you wanted to match the least square error between the linear perceptron, and the architecture was different. There was no sign here, so it's a different situation. And indeed, in that case, we didn't need to go through some iterative scheme in order to find the weights. We could just plug in this formula that involved an inverse of the matrix. Okay. Okay, so another case is so this is if it's classifying correctly, but if yt plus 1 wt transpose times xt plus 1 is smaller than 0, then we change the weights, and this is the key step. Wt plus 1 is equal to Wt plus some number eta, I will explain in a moment what it is, times yt plus 1, xt plus 1. Eta is some number which we can keep fixed during the whole scheme, and it's called sometimes the learning rate. And you just decide on it. It's some number. It's called learning rate because it kind of sets the magnitude of the changes that we make in each step in which we're modifying the weights. Okay, so the larger eta, we make more significant changes in W. Now, this formula is important, and we need to understand first why it makes sense. So can someone tell me why it makes sense? Hmm? So let's ask ourselves, we make the change in W. Why do we want to make the change in W? Because we want to classify correctly this example, which we did not classify correctly with the previous weights. So what we want to see is that this change makes it more likely that we're going to classify correctly this example. And this is what you can see. You can see that if you take Wt plus 1, so classifying correct, what we want Wt plus 1 times xt plus 1 to be the same as yt plus 1, so that have the same sign. So we want yt plus 1 multiplied by this thing to be larger than 0, right? And we know that yt plus 1 times wt, the previous weight, xt plus 1, was smaller than 0. But you can see, so you can write what I wrote here as a contribution coming from this part, which unfortunately was negative, plus the contribution that we'll get here. By the way, eta is larger than 0. That's important. So this thing is equal to yt plus 1 wt transpose xt plus 1, which was a problem. It was smaller than 0, plus eta times, what do we have here? There we have yt plus 1 squared, and we have xt plus 1 transpose times xt plus 1. Right? This is, what can we say about this? It's non-negative. It's well, yeah, it's non-negative. And this is also positive. This is 1. Right? Y is either plus 1 or minus 1. And this is larger than 0. So you see that the change that we made in the weights shifts this product towards more positive values. It might not be enough, okay? But it brings us closer to where we want to be, okay? Now, the scheme is that we do this iteratively over all examples. It's not clear that when we do this for one example, we're not going to ruin it for another example. And so it's not clear that doing this iterative scheme will lead us in the end to a situation where we're classifying all the examples correctly. But turns out that the answer is that yes, if the dichotomy can be realized by a binary perceptron, then we will find a possible solution. So let me just finish, though, writing the algorithm, and then I will make the statement more precisely. So I already said that we're cycling through all the examples. Maybe I will add here cyclically. And just 3, stop if we're classifying all the examples correctly. So stop if no update was made in a full cycle. Yes?
So you want to normalize the example in some way, so example larger than 0 will be small?
Not in this algorithm. In this algorithm, we do not do it. Maybe it's possible, but in this algorithm, we don't. Okay, so we stop if there was no update in this in the full cycle, and therefore, if we stop, it means that we have classified correctly with the weight that we have classified correctly all the examples, right? So now there is a theorem, the convergence theorem. And the convergence theorem tells us that if there exists a W 0 such that Y mu W0 transpose X mu is larger than 0 for all mu, then the perceptron learning algorithm stops after finite number of steps. Okay, so if there is a possibility to realize a dichotomy with a linear perceptron, the algorithm will find one. It might not find. Typically, there is going to be many different choices for the W that can realize a particular dichotomy. But so the algorithm will find one of them. And that's not necessarily the one of the W0 that I wrote here. Okay, now, so, yes? Because Y appears both here and here, right? And the same is for X. The X appears once here and once in the weight. So I want to make some comments. And one of them is about this learning rate. So I told you that you can pick the learning rate to be whatever you want, and this will work. Okay? And we might discuss other situations in which we try to optimize, do something a bit similar to find some optimal weights for a more complex architecture, and learning rates might matter. In this case, it doesn't really matter much which learning rate you use, and I want to explain a bit why that's the case, or think about it in a little bit, in a slightly different way. So what will I do? I think that I will erase this because I want you to have the expressions over there. So any value of eta can be used, and what I want to point out is that in some sense for the linear perceptron there's a reason why the eta doesn't really make a difference. Maybe you can understand it. Yes?
No, that's about the convergence
Ah,
theory.
yes.
So if I'm running the algorithm and did not stop, I don't know if I did not converge yet or if there is no W in between.
Right. Yeah, it's true. So I don't know the answer. I should. It's a good question. Is there a way when you're running the algorithm to tell that it's not realizable, but that the dichotomy is not realizable by a linear perceptron, and so the question really is whether there's some bound that you can possibly there's some bound that you can infer from what's going on about how many iterations you might need to go through until you converge. And I'm not sure about the answer. Maybe it's a good homework exercise to have you think about it. I suspect that there is a way, but right now I don't know the answer. Okay. But for what is clear is that if you stop, you know that you found an answer. Okay, so but I will pose to you another question. Why is it that eta doesn't really matter much? Yes?
Maybe because we don't need a specific, an exact output that may be time.
Okay. I think that I'll give you a hint that the answer lies in this expression. The expression is just for the output, what the binary perceptron does. Yes.
So basically, all you care about is the direction of the W.
Exactly.
And,
So
you take some linear combination, and the exact magnitude would.
yeah. So that's exactly what I wanted you to say. What Leo said, that by definition, the magnitude of W doesn't matter at all for the binary perceptron. If you multiply W by some factor, it does the same thing, right? Right? So, in some sense, what eta is setting is what is the magnitude of the W that we're going to get. Doesn't really matter much, but it's a bit more subtle because there's an interplay. What really matters is not eta, but somehow the ratio of eta and the initial W that we chose. So we chose some initial W0. Where did I write it? Here. Some initial W0. And what eta is really setting is what is the magnitude of the corrections that we're going to make compared to the initial W0. Another way to say it is that if we would multiply W0 by some factor and multiply eta by the same factor, we're going to end up with the same set of perceptrons as we update the weights along the way. So instead of asking why it's not important which eta you choose, you might just as well say, why is it not important which initial W0 you choose? So it's exactly the same question for the binary perceptron. I can't give you the answer. I mean, the answer lies in the proof that the binary perceptron converges. But in some sense, again, for the binary perceptron, the choice of the learning rate is completely equivalent to the question of what is the choice of the initial condition, because it's really the relative magnitude which is important. Okay, the other more important comment so maybe I will just write that this is equivalent to any W0 can be used, a non-zero W0. Okay, the more important comment, maybe it's so important that I will do it here, is that we're here in this course not to learn machine learning. We're in this course because we want to think about the brain. And this update rule that I proposed here, I claim, has a very nice, neat interpretation in terms of plasticity. So if we really take seriously this architecture as representing a neuron which is connected to a set of input neurons and is updating its weights, the synaptic weights from the input neurons to the output neurons, there are several very attractive features of this rule. What are the attractive features? What are the nice features in this rule?
Takes into account that postsynaptic.
Exactly. So it's really, you can imagine that we gave the inputs to the neuron. We checked what is the output, right? And now the updates to the weights is depending only on the inputs. So the updates to the weights from this unit, say, to this unit, depends only on the activity of this unit. It depends only on the activity of the output unit. So it's a local rule. There is something which is non-local in it. What is the part which is not local? The decision whether we change or not, right? Because there are two cases. There's a case where we don't make a change, and there's a case where we do make a change. But we can imagine, but this is the same for all the synapses. So we can imagine that some signal saying whether we need to make a change or not to make a change is transmitted to all the synapses through, say, a neurotransmitter. Okay? So let me write this a little bit differently. Okay, it's not in my notes here, but I will just do it. So we can say that Wt plus 1 is equal to Wt. So now let's write it for instead of a vector in vector notation, let's write it for one of the synapses, one of the entries in W. So Wi t plus 1 is equal to Wi times t plus some signal that I will call R. And the R will depend on whether we classified correctly or did not classify correctly. So R will be either 0 or 1. So R will be reward signal 0 or 1. And this multiplies eta times yt plus 1 xi t plus 1. So it's local because it's the same I appearing here, here, and here. Okay? Depends only on the presynaptic neuron, the postsynaptic neuron, and there's some reward signal. Let's see. We have 5 more minutes, so I will not prove to you now that the learning algorithm converges. maybe I will discuss one very simple generalization of this. So I will prove it to you in the next lesson on Tuesday, that I will prove the convergence theorem. What I want to just do is a very simple generalization, which is a perceptron with a bias term. So we could imagine that we generalize our architecture slightly, and instead of saying this, imagine that y is equal to the sine of W transpose times X plus some constant. So this corresponds in terms of what we geometrically do. Instead of having a hyperplane that goes through the origin, we're now allowing the hyperplane to be shifted, not to go through the origin. So in 2 dimensions, an example will be a classification like this, where the separating plane, in this case a line, is not going through the origin. And so we can ask ourselves, what do we gain by doing this? Obviously, the capacity should become larger, right? We added another degree of freedom, so we certainly can realize all the dichotomies that we realized without a B, but maybe we can realize some more. So now we have the choice. So now we have the choice to choose both the W's and the B. B is one number. So we have one more parameter that we can play with. Therefore, we would be able to realize more dichotomies. Okay, so it turns out that what we know about the case, about the perceptron without a bias, is all we need in order to understand this example, because we can think of this problem with a set of examples x mu and weights w, which are n-dimensional, and we can map it to another problem where we have input vectors which are n+1 dimensional and weights which are n+1 dimensional. And so our new x mu's, which are going to be n+1 dimensional, are going to be vectors which have x mu in them and just an entry equal to 1 here. And our weights, our new weights, okay, we map these two pictures. Our weights in the n+1 dimensional case are going to be the weights that we had here and B. And you can see that if we now think about this as a perceptron without a bias, the sine of W tilde transpose times X tilde, we need here both the sign of a vector and the tildes, right? So tilde here and line and the tilde bar and the tilde here. What is that? It's equal to the sign of X transpose W transpose X plus actually it's I should put here, I think, plus B. Yeah, plus B. So what we've just done is that we mapped the problem with a bias to the n-dimensional problem with a bias to n+1 dimensional problem without a bias. And so, there is a direct mapping between the two. And therefore, the capacity with bias is simply equal to the capacity without a bias for p points in the n+1 dimensional case, and which is indeed larger this is larger than CPn. Okay, so it's very easy to understand what is the capacity. And I think, I think I'll stop here, and I will see you again next week.